All right, guys, welcome back. This is going to be part 3 of the 7.5 instructional videos. The first couple introduced the idea of graphing inequalities. I believe those were from Khan Academy. I think they described and summarized the process in a shortened video very well, so I went ahead and used them to kind of introduce the idea of graphing inequalities. And what we're going to do here is we're simply going to dive more into the concept. I'm going to focus more and more on examples and the practical way that we do this. If you want to learn more about kind of the why behind how we graph linear inequalities, or you want a refresher on the introduction, again, go back and watch those 2 Khan Academy videos. So what we're going to start with is we're going to graph y is less than 2x plus 8. And I think in order to understand this, maybe it's better if we first look at graphing y equals 2x plus 3. Okay, we're going to graph y equals 2x plus 3. This is an equation in slope-intercept form. Again, I know it's an inequality, but right now we're going to graph it as an equation. So to graph this, I would go up 3, and I would go up 2 over 1, up 2 over 1, up 2 over 1. I would go down 2 left 1, down 2 left 1, down 2 left 1. And then what I would do, again, I know I'm going to graph the inequality in a bit, but if I was graphing this as a line, an equation of a line, what I would do is I would connect all these dots with a line. And then as we have discussed before, what does this line mean? Well, what the line is all the potential solutions, all the potential ordered pairs that make this equation true. It's all the potential solutions. How can you tell? Well, if I pick a point on this line, let's say I pick negative 1, 1 here, and I plug it into the equation, 1 going in for the y and negative 1 for the x, what I'm going to end up with is a true math statement. 1 equals 1. Okay? And this should make sense, right? What our line represents here is all the potential solutions, all the potential x, y pairs that will make that equation true. Okay? If I picked a point that was not on the line, negative 2 or negative 3, 2, for example, negative 3, 2, for example, and I plugged that in, I will get an untrue math statement. Here, I would get 2 equals negative 3. And of course, that is not a true math statement. Okay? And that should make sense. Again, what that means is negative 3, 2, since it does not satisfy the equation, it should not be a point on the line. Okay? It's not a point on the line, so it doesn't satisfy the equation. All points on this line, whether they're the nice, neat, even integers where the red dots are, or if they're the decimals in between, as you can see indicated by the blue line, any point on that line will make the equation true. And this is our basis for graphing lines. But again, we're not really interested in graphing lines. We're interested in graphing an inequality. Well, to graph an inequality, again, as you've seen, what we are going to do is we are going to start We're going to start by graphing just like you normally would when you're graphing a linear equation, where we're going to recognize that our inequality is in slope-intercept form. We're going to go up 3, then up 2 over 1, up 2 over 1, or down 2 left 1, down 2 left 1. And again, I think what's helpful in this is if we think about our goal, what our goal is that our graph represents all the potential solutions, all the potential values that make this inequality true. All the potential values that make this inequality true. Now, if we take a random x value, let's say we take 0, when x is 0, what our inequality would say, and you saw this some in the Khan Academy video, is that y needs to be less than 3. When x is 0, y needs to be less than 3. Any y value less than 3 will satisfy that inequality. Now, if it was an equation, if we were still working with the equation, what would happen is we would plug in 0 and it would say, hey, y needs to equal 3. And it would only be the point on the line. But with the inequality, what we see is y doesn't need to equal 3, y needs to be a value less than 3. So when x is 0, all of the y values that are less than 3, all these ordered pairs indicated by this blue line, will satisfy the inequality. If I picked a different x value, maybe I picked x is 1, I find that all the y values when x is 1 need to be less than 5. And so all these all these coordinate pairs indicated by my second blue line would also satisfy the inequality. And if we keep going and we do this, what we're going to end up with, as we saw in the Khan Academy video, is a massive shaded region. A massive shaded region. And where we're really going to end up seeing, it's not just for those green dots, it's all the points in between, that the graph of our inequality will be this large shaded region. And it will be a large shaded region bounded by these green dots, bounded by the outline of the graph of the line y equals 2x plus 3. That line will act like the boundary for the graph of our inequality. So it's all of these points below the line, broadly speaking, all the points below the line y equals 2x plus 3, which you can see outlined in green, will make up the graph of y is less than 2x plus 3. Now the question is, okay, all the points below the line will make up the graph for y is less than 2x plus 3, but what about points on the line? Well, again, what a graph is it displays all the points that make the equation or the inequality true. So let's pick a point on the line. Here I'm picking 0, 3. And let's see if it makes the inequality true. Well, when I plug in 0 for x and 3 for y, which is a point on the line y equals 2x plus 3, I end up with an untrue math statement. 3 is not bigger than 3. So while the line y equals 2x plus 3 is going to serve as a boundary for the shaded region that represents the graph of our inequality, points physically on the line will not be included in that region. So how do we draw a graph that has a boundary at y equals 2x plus 3, but we don't want the points physically on y equals 2x plus 3? Well, we're going to create a dashed line. And this is what the graph of our inequality y is less than 2x plus 3 should look like. As we saw earlier, all points below the boundary of the line y equals 2x plus 3 satisfy the inequality y is less than 2x plus 3. This whole blue shaded region contains all the coordinate points and beyond, if we would keep going to the right and down, all the potential coordinate points that'll make that inequality true. But points on the line, while the line y equals 2x plus 3 acts as the boundary for the graph of our inequality, our shaded region, points on the line y equals 2x plus 3 will not make our inequality true. So we will have a dashed line acting as our boundary to indicate to the reader of the graph that no points on the line y equals 2x plus 3 will make the inequality true. And really, this all can be summarized into 3 statements. Okay, you've kind of seen the logic, you've followed the logic, you've seen the logic behind how we graph inequality, some of the theory between this and the Khan Academy video. Here's what it all boils down to. The inequalities that have the open side facing the y and slope-intercept form are shaded above the line. Inequalities that have the open side facing the x are really the mx plus b portion, because we won't always physically see the x if the coefficient of the x was 0. The open side faces the side with the x on it in slope-intercept form. They are all going to be shaded below the line. And you can see I've underlined slope-intercept form. This statement will not be true for equations in standard form. Okay, and this should make sense, right? The open side of the inequality could face away from both the x and the y in standard form, or it could face both of the x and y in standard form. And so this logic of the open side faces the y here, so it means this, that will not apply in standard form. But it does in slope intercept. And so when we graph inequalities, we are going to turn them into slope intercept form. The final piece to this, if the inequality has an equal to sign, fill in the line. If it does not have an equal to sign, please make a dashed line. Again, if the inequality doesn't have an equal to, points on the line will not satisfy, the line being the boundary, will not satisfy the inequality. So while we still want to indicate what the boundary is, that line, we do not want to fill it in and confuse our graph reader into thinking that points on the line will make the inequality true. And can we see these principles illustrated below? Absolutely. If we look at our inequality, y is less than 2x plus 3, you can see that we are in slope-intercept form. The open side is facing the x, and what we ended up doing, even though we more logicked through it before we learned the principles, we shaded below the line. You can also see there is not an equal to symbol, and so we end up making a dashed line as our boundary, where y equals to it, the line being y equals 2x plus 3. Okay, and it's all the points below that line, not including that line. Okay, so again, if you haven't written these down yet, I would pause the video, go ahead and write down these principles. These are going to be the practical processes, the shortcuts, if you will, that you'll use when graphing equations or inequalities when you're graphing inequalities on the coordinate plane. Okay, let's look at some more examples. Let's go ahead and graph together y is greater than or equal to 3x minus 1. Okay, and from now on, I'm not really going to focus on maybe all the theory behind it. I'm going to use those principles to help me quickly graph the inequalities. If you, again, want to know more about the logic behind why we're doing these processes or how they work, you can check out the Khan Academy videos, or you can talk to me in person. So what we're going to do here, we need to graph y is greater than or equal to 3x minus 1. And anytime we're graphing an inequality, it is good to start by getting the outline of the equation, the equation, right? Our inequality is y is greater than or equal to 3x minus 1. What that means is the line y equals 3x minus 1 will be the boundary for our inequality. So let's go ahead and get the outline of that line. See, it is already in slope-intercept form, so I can jump straight into graphing. Again, remember, we would have to get it into slope-intercept form if it was not. And this is the outline of the graph of y equals 3x minus 1. This will act as a boundary for our inequality y is greater than or equal to 3x minus 1. So step one, we're going to graph it as if we were graphing a line, but we're only going to get the foundation of it. Step two, we are going to look at the equal or the inequality symbol. When we look at it, is there an equal to present? There is an equal to present. So we will go ahead and fill in our line. Our line will not be dashed. Our line will not be dashed. Okay, that means any point that is physically on this line will make the inequality true. If you want to make sure you did it right, if you're still unsure about dashed or solid, pick a point on the line and check it. I'm picking 0, -1. And let's see if that makes the inequality true. And indeed, it does. -1 is greater than or equal to -1 is a true math statement. Therefore, points on the line do satisfy the inequality, and we want a solid line as opposed to a dashed one. Step three, what we're going to do, we are going to shade above or below the line. Since we are in slope-intercept form and the open side of the inequality is facing the y, we will go ahead and we will shade above the line. We will go ahead and we will shade above the line. And again, to ensure that I've done this correctly, I can pick a point in the shaded region, make sure it makes the inequality true. I will pick -2, 2. I'm sorry, I flipped my x and y there. And I do get a true math statement, and so I've shaded on the correct side. So this will be the graph of my inequality. I want to shade above because the open side's facing the y and slope-intercept. Solid line because it's an equal to. And again, that boundary is just going to be created by looking at the line y equals 3x minus 1 will act as the boundary. Let's do another example. 3x minus 5y is less than 10. Okay? Now, unfortunately, this one is not in slope-intercept form, so I cannot go ahead and graph it right off the bat. I could, let me rephrase, I could, this is or if I were to graph the line, what the boundary would be, it would be the line, 3x minus 5y equals 10, that will be the boundary. And that's an equation in standard form, which I could graph, but then I'm not going to be able to use my shortcut about what side of the line do I shade on. I just would have to check points on either side. I think it's a little bit easier too, since most people don't like standard form, to go ahead and transition this boundary into slope-intercept. So how would we go about this process? How would we change our inequality from standard form to slope-intercept? Well, we need to get y by itself. That's the y equals mx plus b, y is alone, so that's the hallmark of slope-intercept. So to get y by itself, I'm going to subtract 3x from both sides. And I get negative 5y is less than 10 minus 3x. Then I will divide both sides by negative 5. Again, making sure I divide everything on the left side, right? If you think about a scale, I can't divide one side into fifths and then take part of the other side and divide it into fifths. No, to keep the scales balanced, I have to divide both sides into fifths, or divide them by 5. And so what I'm going to do when I divide everything by 5, notice also I divided by a negative 5, so my sign is going to flip. My sign is going to flip. And I get negative 2. My negative divided by a negative is a positive, so negative 3 divided by negative 5 becomes positive 3 over 5. X, and I'm not going to turn that into a decimal because I think since that's my x coefficient, it'll be easier to graph it using rise over run with a fraction as opposed to a decimal. So I started solving this or graphing this inequality by turning it from standard form into slope-intercept form. Now that my inequality is in slope-intercept, I can go ahead and graph it. Of course, I'm going to start that by creating the boundary. Go up 3. Over 5, up 3, over 5. And now I'm not going to connect them with a line because, again, this is an inequality. So what I'm going to do before I ever draw a line is I'm going to look and I'm going to say, okay, there is no equal to there, which indicates to me, according to my shortcut, that this should be a dashed line. Right? And what the dashed line indicates is that while the line itself, y equals negative 2 plus 3 over 5x, is the boundary for the inequality. Points on the line don't satisfy the inequality. You could check that by plugging in a point on the line like 0, negative 2. And what you will end up with is an untrue math statement, further indicating that points on the line don't satisfy the inequality. Negative 2 is not bigger than 2. And so what I'm going to do now that I have my dashed line, I'm going to look and I'm going to say, okay, what does my shading need to be? Well, the open side of my inequality is facing my y, so I will shade above the line. And again, I know I'm not filling this all in, but in a perfect world, all this shading would be filled in. And again, what that means is any coordinate point in that shaded region that is not on but is above the line y equals negative 2 plus 3 over 5x will, in fact, make the inequality true. Okay, if you're not sure, pick a point. I picked 0, 1. Plug it in. I would highly recommend plugging it into the original inequality That way, in case you made a mistake in your algebra in transitioning from standard form to slope intercept, hopefully that mistake will come to light. If you just plug 0, 1 back into y is greater than negative 2 plus 3 over 5x, any mistake in your algebra will not come to light. So what we want to do is plug that into the original, see if we made any mistakes, whether in our algebra or just in our graphing. And when I do this, I get a true math statement indicating that yes, I have shaded the correct region. These points that are above the line, the boundary line, 3x minus 5y equals 10, any point above that will make the inequality true. Let's look at one. So in this example, I am hosting a cookout. I plan on spending no more than $24 on my entrees. At Kroger, hamburgers are on sale for $4 a pound and chicken wings are $2 a pound. I want to make a graph modeling the situation above and identify 3 possible combinations of hamburgers and chicken wings I could buy without exceeding my budget. So how could we figure this out? Well, I'm hosting a cookout and I plan on spending no more than $24 on my entrees. So $24 sticks out to me, and not just 24, but the phrase no more than. No more than. What does no more mean? It means 24 is the top end of my budget. So instead of writing an equation, right, I'm not spending exactly 24. I just can't spend no more than 24. So I'm going to have the open side of an inequality face the 24. Why? Because this will indicate that whatever is making up my $24, I can't exceed the $24. If you accidentally put your inequality the other way, it would indicate the opposite. It would indicate that 24 is the minimum amount that you have to spend, which is not the case. I also can put an equal to underneath. Why can I do that? Well, what I'm saying here is that for the $24, I can equal it and still be okay, right? When we read the English phrase no more than $24, if I told you I spent 24, that would be okay because it's not more than 24. It's right on the nose. So it's 24 is greater than or equal to. Now I need to figure out what's making up my $24. Well, I'm buying hamburgers and chicken wings for my entrees, and that's what the $24 is for, my entrees. I'm doing hamburgers and chicken wings, and I know that hamburgers are $4 a pound, and chicken wings are $2 a pound. But what I don't know is how many chicken wings and how many hamburgers I buy. So maybe I put some variables in there, and again, I'm using X and Y. I want to make sure I label them. So maybe X is my number of pounds of hamburger I get, and Y is the number of pounds of chicken wings I get. And then let's pause and make sure our work makes sense, right? 4 times the number of pounds of hamburgers I get will give me the total amount I spend on hamburger. 2 times the number of pounds of chicken wings I get will give me the total amount I spend on chicken wings. Add those together. It's got to be less than 24. Seems to make sense so far. And now we have a linear inequality representing our scenario. We're supposed to make a graph of the situation, but when I look at my linear inequality, what I notice is that it is not in slope-intercept form. And when we graph linear inequalities, we want to graph them in slope-intercept. So what I need to do is I need to get y by itself in order to have my linear inequality in slope-intercept form. So subtract 4x from both sides. And then I will divide everything by 2. And I get 12 minus 2x is greater than or equal to y. 12 minus 2x is greater than or equal to y. Okay, now my inequality, my linear inequality is in slope-intercept form, so I can graph it as I was instructed to do. Maybe because of the size of the numbers, the 12 being that y-intercept, maybe I change my scale a bit. My grid lines will go up by 2s. But my rise over run currently is going to be down 2 over 1, so I'll probably still Make my grid lines go by ones on the x-axis. Just change them a little bit on the y. And so I'm going to plot my y-intercept at 12. Then I'm going to go down 2 over 1, down 2 over 1. Again, notice it looks like I'm only going down 1 over 1, but that's because I changed my scale. Be very careful whenever you change your scale. I notice that this graph is this inequality is in equal to, now that I have my boundary line all set. I notice my inequality is in equal to. So I go ahead and draw a solid line indicating that all points on the boundary will make the inequality true. Well, what you may notice is different about this one that I did compared to the others. I don't have arrows extending the line forever. Why? Well, we need to remember context in our word problems. If x is the number of pounds, of hamburgers, right? If this is the number of pounds of hamburgers and y is the number of pounds of chicken wings, we can't have negative number of pounds of chicken wings or negative number of pounds of hamburgers that we buy. So we want to keep our graph in the first quadrant, again, interpreting in that context. And then finally, what we're going to do to complete the graph of our inequality is we are going to fill in. We're going to shade. And since the open side is facing the x, this means I will shade below my line, my boundary line. I'm going to shade below it. And there is the graph of my linear inequality. Restricted to the first quadrant because of the context, but that's what my graph should look like. Any point on or below the line in the first quadrant will make my linear inequality true. Okay? If I wanted to check my work, I could pick points either in that shaded region or physically on the boundary line, plug them into my original inequality, make sure that I have done it correctly. We won't do that right now, but that is something you could do to check your work. And our final step that we are instructed to do is to figure out 3 possible combinations of hamburgers and chicken wings without exceeding my budget. What are 3 possible combinations without exceeding my budget? Well, any point, if the linear inequality represents all the potential solutions, then any point in the shaded region or on the line, because the line is filled in, will make my inequality true and consequently will be a combination of hamburger and chicken wings that will not exceed my budget. So I could pick this point, which is 1, 2. Again, don't forget that changing scale. What does that mean? That would be 1 pound of hamburger, 2 pounds of chicken wings. I could do that without exceeding my budget. Or I could do maybe 2, 6. That would not exceed my budget. Or I could even go up here and I could do 1, 10. And that would not exceed my budget. That would be right on. That would be right on my budget, but it would not exceed it. And again, I think while these are all potential solutions, I think it's important to think about the context of the problem. If I'm hosting a barbecue, even though it's fitting my budget, I probably don't want to select 1, 2, because it's probably not going to be enough food. So even though I met the criteria of meeting my budget, according to the context, probably don't want to go with that. I probably want to maximize my budget, so probably 2, 6 is a better option, or maybe if we have a lot more chicken wing fans than we do hamburgers, maybe 1, 10 is where I want to go. So any point in that shaded region will be a combination of chicken wing and hamburger pounds that I could get that would fit my budget. But again, we want to make sure our answer makes sense. Guys, thanks for watching. Let me know if you have any questions.